All right, what up, programmers, coding people, YouTube? This video is going to be going over time complexity, a little bit of space complexity, some Bagel notation. I want to drill these concepts into your mind. I actually haven't made a video on this yet, surprisingly. So I want to get people to understand this stuff. Why do we even care about it? I guess we'll start there. But I do want to say I'm making this video because I think a lot of the videos out there, which there are some good ones, but people dive too into detail. So I am going to dive into detail. I should give you examples and stuff, but sometimes a tutorial or explanation can get ruined by trying to say every sentence right, so you don't get any criticism at all in the comments. But I am not going to, I want to make this more understandable. I'm going to explain this. For example, in this tutorial right here, where I'm going to tell you about time and space complexity, I'm going to pretend that one loop is a second. Like it takes a second to loop through each element of an array, because I think that's easier to understand. Whereas, some people might try and more accurately, precisely measure that. I'm not going to do that because it's way more easy to understand if we just think of a loop as a second when we're talking about time and space complexity. So why do we care about time and space complexity? First of all, if you are interviewing at any of the top companies, a lot of the standard interview process at probably half or more of the companies that you're going to be interviewing at, you're going to have to write some kind of algorithm or program that solves something, and you're going to be asked to explain the time and space complexity. And why? Why is this important? Why is this even in interviews? Well, a program when we're programming, we want it to be fast. If you're a software engineer and you're given a list of 20 elements, you can see this array right here, 1 through 20, and your boss says, hey, today's task, you got to go print every element of that array. Can you do that? And you write an algorithm that says, sure, boss, it's just going to take 3 days. He's going to be like, 3 days, dude, you could loop through that. That should be instant, So that's this is a better algorithm, just looping through the array and printing each number. That's very, very quick compared to, you could potentially write an algorithm that takes a really long time. So you want the program to be fast for obvious reasons. You want things to be done fast. Memory-wise, you want to use as little memory as possible. It's kind of just obvious stuff. You don't want to use memory, and you want the things to run fast. When we want to we write programs to automate, we write programs to do things. We want those things done fast. When would we want them done slow? That literally is never the case. And we don't want to use memory because that's resources, right? So we don't want to use time and resources. Want them as low as possible. Okay, we get it, Nick. We get it. Quick side note, I did make this video with the intention of making a digestible way to understand Bagel notation, time complexity, space complexity, at least the basics. So if you watch the whole thing through, you should understand these things. But I do want to stop to take a second for the sponsor of this video, which is algoexpert.io. AlgoExpert is a platform dedicated to helping engineers pass their coding interviews. And yours truly is actually an algorithms data structures instructor on the platform. I just released 5 new questions. There's 110 questions up. These questions are curated to be some of the best and most useful questions to get the most information out if you're trying to pass an interview at one of these companies. There's multiple instructors on the platform now, including other YouTubers you might know, Clement, Tech with Tim. There's tons of great features on the platform, and you could actually solve and write code right on the platform. They have different kinds of text editors you could choose from, and there's tons of language support if you want to choose different languages to solve the problems. And then the best part about the platform is the video explanations that come along with each question. So with each question, there is a video tutorial where we go over a conceptual overview, talk about time and space complexity of different solutions, and then there is a coding portion walkthrough. So if you want to check it out, go to the link in the description. That is algoexpert.io/Nick, and you can get a 10% discount. And go pass your coding interviews. All right, back to the video. All right, so we understand why time is important and space is important, but when we write a program and our boss asks us, or the interviewer asks us, how fast does our program run? If we have an array of 20 numbers here and we want to print every number in the array, when they ask us how much time and space does it use, we're just doing a for loop here. We're not going to say, oh, this executes in 20 seconds and uses 1.2 megabytes of memory for the counter. No, we're not doing that. What we use is this thing called Bagel Notation, which you might have heard before. And if you haven't, well, then good, because this is a good spot to hear from. You can get confused when people talk about upper and lower bounds and big omega and all that crap. Forget about any of that. What it really is just O and then a variable. And this variable is key here. We usually use n, so usually you're going to say O of n squared, O of n log n, O of log n, but n represents, what n represents is anything. Usually it is the data size, or the whatever you're using for data. So if we're given an array here, in this case, n would be the number of elements in this array, but n is anything. N could be the number of nodes in a binary tree. N could be the number of nodes in a linked list. N could be the number of characters in a string. N could be the number of elements in the array. N could be anything. You have to say what n is. So when they say, what is the speed? What is the time complexity of the algorithm that you wrote to print every element of the array? And I'm doing a for loop. I loop through every single element. You can see here. If we had an array of size 20, it would go 1, 2, 3, 4, 5, 6, and it would print every single one of those numbers. In a for loop, it looks at every single number. So I'm going to say my program here runs in O of n time complexity. And I'm going to tell them, the interviewer or my boss or whoever, where n is the number of elements in my array that I'm using, or the input array or whatever. I get to choose what n is. I'm going to tell them what n is. So if I'm looping through an array, I'm going to say n is the number of elements in the array. And this is referred to as a linear time complexity, where you look through every element of the array, because as you add elements to the data that you're looking at, the time goes up in a linear fashion exactly at the same pace. So if we have an array of size 1, since our algorithm is just looping through all the elements, it's looping through one element. And if it's 1 second per loop, that's 1 second to execute. If it's 5 elements, 5 seconds to execute. 10 elements, 10 seconds to execute. 20 elements, 20 seconds. So as you add elements, 21 seconds, 21 elements, 21 seconds to execute. It's directly proportional. As the data gets bigger, the time complexity grows at the exact same rate. And that's why it's linear. As time goes up, as data goes up, so does time. So that is kind of the idea of Big O notation, is you get to pick what the variable represents, but also it's in relation. We're talking about the relationship between time and data. So how does the time grow as the data set gets bigger? Okay, cool. Now, there's many different time complexities. So this article is great. These are the most common ones. This is basically all you're ever going to look at in your career. There is constant time. Constant time is just some kind of calculation. There's no data size we're dealing with or data that we're dealing with. It's just like 5 plus 5, for example. If in your algorithm, for some reason, we wanted to print 5 plus 5 in the loop, that is a constant time thing. That doesn't go up. There's no extra time as the data scales. There's no change in that value. It is constant time complexity. Another common one is log of n. We'll get into that in a second. Linear, we just went over, n log n squared, 2 to the n, and O of n factorial. This article I'm linking in the description. Read through this article, but these are the main time complexities you'll ever have to deal with. You could see they labeled it here perfectly for us. Horrible. These are bad time complexity. That means they take a really long time. And then these are better time complexities down here. They put linear and fair. They put these ones at the best. Okay. Now, let's get into n squared, the next most essential time complexity and common time complexity that you guys need to understand. Okay. All right. So for an example here, here's an algorithm that is n squared where we're printing elements. And we're printing 1, for example. And let's say we're doing this on 1, 2, 3, 4, 5. We print 1. You see this outer loop here. We print 1. Now, once we print 1, we print every element in the array. So our output is 1, and then we go through the whole array. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then we print 2, because it moves on to the next iteration of the outer loop. And then we print 1, 2, 3, 4, 5. And then we go to 3, and then we print 1, 2, 3, 4, 5. So you could see how this is n squared, because for those n iterations where we saw an outer loop, this one simple for loop that's just 1, 2, 3, 4, 5. If n is the length of the input array, well, then that is O of n. This is O of n, but 1, and then times O of n, because we're doing that O of n within an O of n. So nested loops, most of the time, they are n squared. However, don't always take that for what it is. You have to look through what you're looping through, right? On our outer loop, we're looping through the input array, and on our inner loop, we're also looping through the input array. So if n is the elements in the array, yes, that's O of n squared. But let's say we have 2 arrays. One of them is 1, 2, 3, 4, 5, and then one of them is just 1 and 2. If we're looping through, and this one is called array 2, and then this one's called array 1, if this is looping through array 1 and this is looping through array 2, these are looping through different things. So if n, when you tell them the time complexity is the number of elements in this array, this is not an O of n squared algorithm, because this is not doing O of n times O of n. This is doing O of n times a different variable if it's looping through this array. So you would say something like O of n times m. So you'd make a new variable. You'd say where n is the number of elements in this array and m is the number of elements in this array. So it's n times m. And that should really solidify what this n squared thing is, how these algorithms are kind of working. I really hope it does. Okay, so let's recap what we learned so far. O of n is where we have the time going up in a linear fashion with the data. As an element gets added to the data set, a second gets added to the time. O of n squared, however, is n, it's taking the number of elements and squaring that to get the time. You could see one element is 1 second, but as the data goes up, there is that steep curve right there. You could see 1, 2 elements is 4 seconds. 3 elements takes 9 seconds, because if n is 3, n squared, 3 times 3 squared is 9. 4 elements is 16. 5 elements is 25. Look how fast this is increasing, the seconds. So this is a slow algorithm. We deal with huge data sets when we're actual software engineers. So if you're dealing with a data set of 10,000 elements, or if you're dealing with a data set of 1,000,000 elements, well, then an n squared algorithm is going to be 1,000,000 seconds times 1,000,000 seconds, and that could be forever. So that's why we want to reduce this algorithm. Now, one thing that is an n squared algorithm is calculating the frequency of elements in an array. And by frequency, I mean if we have an array and we're given the task to, let's say we call this frequencies. Let's say we have this array and we're told, hey, find out how many of each element there are in this array. Find out how many 1s there are, how many 2s there are, how many 3s there are, how many 4s there are in this array. And we could see right here, there's 1 1, 2 2s, 2 3s, and 5 4s, I think. And we want to figure that out. Well, you could do an n squared algorithm, right? Right here. You loop through each element, then you loop through the whole array and see how many of those elements in the outer loop are there. You have a counter, and there you go. N squared, right? A nested loop, right? We can reduce this. We could totally reduce this, which is awesome, if we just look at this. Look at this. This is now O of n, where we're just looping through every element of the array once. But what are we using here? Well, we're using external memory. You can literally use memory, and this is very, very common in algorithms and data structures and time, space, all these interview questions. You use a data structure, a structure for data, and you store results or you store some pieces of data to speed up the performance of your algorithm. We don't always want to do this because we might not have the memory, but if we have the memory and we know that, and our algorithm is super slow right now, like n squared is slow, right? We can get it to O of n by just using a hash map or a dictionary, for example. So we have this dictionary, right? And we can just keep track of the count. We could put elements into the dictionary. So we see a 1. Oh, we see our first 1. Let's put that in there, right? We put it in the storage. And then we see our first 2. Okay, put that in with 1. Oh, we see 2 again. 2's already in there. So let's increment the count. Oh, we see our first 3. Let's put it in there with its initial count. Oh, we see another 3. Let's increment the count. Oh, we see a 4. And this is just looping through the array and incrementing the counts inside of a data structure. So instead of doing that n squared loop, which is really slow time complexity, bring our time complexity down by using data. So you have to think about these trade-offs when you're writing programs, how much memory you have, how much time you want to use. And in an interview, think about this stuff. Now, and cube, for example, would be looping 3 nested loops through the array, right? So as you nest loops, just remember that you want to look at what you're actually looping through, because it doesn't always necessarily mean n cubed if these are different arrays. So we remember that. And you can make up more variables as you go. If it's array 1, if these are all different arrays, then you could say the time complexity is O of n times O of m times O of what element O? Do I know my alphabet? Wait, O of n times... We could say O of L. All right. I guess it was going backwards, right? I thought it was going forward. Okay. That makes me untrustworthy not knowing the alphabet. All right, dude, I'm stupid. But... all right, so we understand what O of n is. We understand n squared, n cubed, constant time. We know we can reduce our time by using memory. What about O of log of n? What does that even mean? Logarithms. I haven't heard that since whenever, algebra or whenever you learn that. Well, logarithmic algorithm is really good. Log of n is really good. And this is a pretty rare time complexity. You're going to see it in a few things, but binary search being probably the most popular, where if we have a sorted array, so if we have 20 elements, you could see it's sorted, meaning 1, 2, 3, 4, it's sorted in increasing order. And let's say we're told to find the number 15. Well, if we don't know what's in the array, what we could do is we could loop through the array. And we could say, okay, if we found the element, if the current element we're looking at is equal to 15, we found it, and we'll return the index. So that takes 15 loops, 15 seconds to get to 15 if we're doing just a loop through the array. That's a long time. So now what binary search does is it says, okay, let's look at the middle of the array, right? We know the length of the array. The length is 20. So we'll take the length, divide by 2. 20 divided by 2, 10. And look at that. We're at the middle of the array. And we're going to say, hey, is what we're looking for greater or less than what the middle of the array? So at the middle of the array, we have 10. 15 is greater. Since it's sorted, and binary search only works on sorted arrays, we know it's on the right side. We know it can't. How could 15 be before on the left side of 10 if it's sorted? It's all less than 10, so 15 is not less than 10. So it's logarithmic is when you're eliminating half of the search space. So like binary search, we're eliminating that. Screw it. It doesn't even matter. We'll never iterate over any of those values. We know it's not there. And then you look at the middle of the new search space and boom, 2 iterations. It took 2 seconds to get to 15. And if we did it in the linear loop, it would have taken 15 seconds. Now, this is extremely good algorithm for huge data sets. For example, the main example is if you have a phone book with 2,000 pages, massive phone book, however many pages there are, and you're looking up someone's name, if their last name starts with an S, you're not going to go page by page till you get to S. You're just going to flip halfway, say, oh, I'm at M. S is clearly on the right side of the book. Flip halfway again until you get to S. That's literally a binary search. It's a sorted book of names. So logarithmic is eliminating half the search space. Now, the opposite of logarithmic would be exponential, like 2 to the n. So this is really bad. Logarithmic, really good because it's super fast. 2 to the n, really bad. Now, in this article, they give a really good explanation. Algorithm is said to have exponential time complexity when the growth doubles with each addition to the input data set. And the growth does double, and there's just so much repetition in the Fibonacci. Like, you could look here at all of these repetitive calculations. Like, if you look, see 4, look at this tree structure. This 4 tree structure is right here. This 4 tree structure is right here. And what you'll learn eventually is that you could use data like dynamic programming to store, like the first time you do the calculation for 4, store it in a data structure. So if you do it over here, and then you'll have it for when you calculate it over here. So like there's a lot of things with really bad time complexities. O of n factorial rarely comes up, but there's a lot of really bad time complexities. We want to get down to really good time complexities. I don't think I want to confuse you with a lot of, the higher level ones. The main ones you're going to deal with, we already went over. N log n is one we didn't go over, which is like sorting algorithms. The best sorting algorithms are merge sort, quick sort, heap sort. Those get to n log n. However, in certain scenarios, very specific scenarios, there are things like radix sort, bucket sort, counting sort, where you could get to linear sorting. But those are very, very like niche and specific cases. So the thing you need to understand is that there are upper bounds, there are there are best case scenarios, right? Printing every element of an array, you can't get that faster than O of n. I can't print every element of the array in constant time, for example. Like, you can't push it. You can improve algorithms, but you can't keep pushing it to the point where you can increase it. There's a certain point where like you're at the best possible one. So like the optimal solution is what you call that in a coding interview. And I hope I kind of made this clear for everyone. Like space complexity is the same thing. If you have an input array that looks like 1, 2, 3, 4, 5, and then, maybe we use a stack in our approach and we keep track of these values and we put them into the stack. Well, if we use every value, if we're talking about O of n as the number of elements in the array, and then we use extra space like a stack where we put every n element in the array, we use O of n space. Now, if we kept track of a 2D array where we kept pushing the input array of size n onto this like main array as space, because we had to do some kind of calculations, that'd be O of n squared space. And you could kind of figure it's like the same thing for space complexity. I hope I kind of made it clear. The main things I want everyone to take away and focus on from this are O of n squared, knowing that every double for loop isn't O of n squared, knowing that you have to look what you're looping through, and just thinking about what the variables represent and kind of understanding that. That's like the main takeaway, not to confuse you with too much. Now, I will say this article, which I'm linking in the description, these were really helpful for me when I was getting into programming at first. These little charts right here, they show the time and space the time complexities of the data structures. So like there's a million data structures, of course, you might not know, but yeah, there's a bunch of data structures that we use to make algorithms faster, or we use in certain scenarios. And it shows you that these methods, they're like the data structures have methods that do things, right? When you use built-in methods, like a built-in sort, that takes time. A built-in index of, or last index, where you get the last index of an element in an array, that takes time. This isn't instant stuff that is just happening magically. Those have implementations behind the scenes in programming languages. So those take time. These data structures all have things like accessing an array. There's indices in an array, so you could access instantly. Boom. But in a linked list, for example, you can't do that. There's no indices. You have to loop through the array to get access to a node or a value. And deleting and inserting into an array shifts all of the values because the indices get messed up in the array. So that's O of n. That's like a whole shift. But for a singly linked list, it's constant. So you can just add things on and it's completely fine. So if you want to think about what kind of program you're writing. If you are inserting a lot and you need some kind of data structure to handle data, or you're inserting a ton, maybe use a singly linked list. If you're accessing a lot, maybe use an array, for example. But there's a ton of this stuff that you could look up. Binary tree, a lot of logarithmic stuff. So just a lot of stuff. Then it has like this chart down here just of the basic sorting algorithms where you look at, and there's like counting sort, radix sort, and stuff like that. And really cool. That's kind of like my rundown. If I didn't get everything specifically right, I think it's fine, because I think I did a good job explaining it in a digestible way that is a little bit easier to understand than like having the specific every single detail right. So hopefully you guys understood. Let me know if you did. Let me know if you didn't, I guess. And if you didn't, that sucks because this is a long video. Like and subscribe. Appreciate everyone that watches. And yeah, that's it. Join the Discord in my thing and follow me on Instagram and Twitter. All right. Peace.